Right now, one of the greatest mysteries in modern mathematics sits unsolved. It's called the Riemann hypothesis. This is the Riemann zeta function. It takes input values, s, and maps them to output values, zeta of s. The input values of the Riemann zeta function are what we call complex numbers. Numbers with a real part and an imaginary part. The imaginary numbers extend the real number line to form the complex plane. The Riemann zeta function takes inputs from across the complex plane, and some of those inputs make the entire function equal to 0. These are what we call the zeros of the function, and the Riemann zeta function has two types of zeros. The ones whose location and distribution is understood and proven, called the trivial zeros, and the ones whose distribution is not very well understood, called the non-trivial zeros. We know there are an infinite number of these non-trivial zeros, and that they all exist within the range from a real part of 0 to a real part of 1. But exactly where they fall within this critical strip is a mystery. One solution is proposed through the Riemann hypothesis, which predicts that each one of those non-trivial zeros falls along a vertical line at 1/2. That's a really fancy way of saying that in order to obtain a non-trivial zero through the Riemann zeta function, the input that goes in must have a real part of 1/2. This hypothesis has stumped mathematicians for 165 years. The Clay Mathematics Institute even offers a $1 million prize for the first correct solution. If it were proven correct, the Riemann hypothesis would open the door to solving one of the oldest problems in mathematics, the seemingly random distribution of prime numbers. Whether it's proven or disproven, the Riemann hypothesis will change the mathematical world as we know it. The only question is when that answer will come.